I gotta say that again. So just really quickly, the purpose of this lecture set is to learn how to work with data where you have two explanatory values. So we utilize what is called a two-way ANOVA or a two-way factorial design, where the two in the two-way refers to the number of explanatory factors. We have seen one-way ANOVA, where you have one explanatory factor. Then we talked about completely randomized block designs, where you have one explanatory factor and one blocking variable, or one confounding variable. Now we are in a situation where we have two explanatory factors and neither of them are considered confounding. So we want to analyze we want to check for a difference in means across the levels of each explanatory factor. When we have two explanatory factors, we also have to consider the effect of their interactions. So two explanatory factors essentially mix together to create a set of what we call treatment combinations. So for example, in this particular exercise, we have we have one response variable, which is the distance the golf ball traveled. We have two explanatory variables, the golf ball brand, which we designate as A, B, C, or D, and the club type, which we designate as a driver or a 5-iron. We have 8 treatment combinations that basically just correspond to the mix of the level of one explanatory factor with the level of the other explanatory factor. So for example, driver and golf ball brand A would be a treatment combination. Driver golf ball brand B would be another treatment combination. 5-iron and golf ball brand B would be another treatment combination, for example. So we have a total of 8 treatment combinations, and at each treatment combination, we have 4 replications. Replication just refers to the number of observations that are observed at the treatment combination level. So for this particular example, we are interested in determining if there's evidence of a difference across the levels of the golf ball brand, across the levels of the club type, or across the levels of the treatment combinations, which would be the interaction effect. When we utilize a two-way ANOVA, we have a testing procedure that starts with what is called a model utility test. You can think of the model utility test as being a test, or rather a general test of the entire system that we use as a pre-check to determine if there's any evidence that there is a reason to continue with the other general hypothesis, the more general F-test that we have seen in the past. So for the golf ball data, question A asks us to perform this model utility test. The model utility test, like any other hypothesis test we have seen, is a 6-step approach. The null and alternative hypotheses for the model utility test can be summarized by writing H0, no evidence of a treatment effect, versus HA, there is evidence of a treatment effect. On the second step, we have alpha equals 0.05. And on the third step, we have the calculation of our F value, which in this case is the sum of each of the 3 sum of squares divided by their corresponding, or divided by the corresponding sum of their degrees of freedom, all over the MSE, which is the standard denominator for any F statistic. So in this particular case, we found an F value of 141.4286. And then we utilized the critical value approach and the p-value approach to check to see if this gives any evidence of a difference, which it does. So here we have rejected the null, which means that we have found evidence of a treatment effect. Now what we would do is begin to work on, or we would move to the second step of our testing procedure, and we're now going to test for an interaction. So in part B, we're going to perform a test about the interaction effect for this particular data set. So our null hypothesis for the tests can be summarized on slide 22. So we can write this in a few ways. For example, we can say H naught all alpha, or the alpha beta ij is equal to 0 across all ij. At least one of them is different from 0. We can also write it in another way where we have a more complex formula that makes use of the relationship between the means. Or we can just say something to the effect of there's evidence of an interaction effect, or H0, there is no interaction effect, versus HA, there is evidence of an interaction effect. Any of these null hypotheses would be suitable for what we are trying to accomplish. Okay, so let's keep it simple here. And on step 1, we're going to have H0, no evidence of an interaction effect, versus HA, evidence of an interaction effect. Okay, then on step 2, we would state our significance level, which will be 0.05. And then on step 3, we're going to give our F statistic. The F statistic is available in the F table that's given on slide 25. So for the interaction test, the F value is 7.452. So on step 3 here, we're going to have F is equal to 7.452. Okay. And now on step 4, we can take again either the critical value approach or the p-value approach. So if we take the critical value approach, okay, I'll have to make a little smaller sketch here. Okay, so here's our F curve. Okay, so we're going to have an F value on 3, 24, and 0.05 in this case. Okay. So notice that for the test of interaction, this is really running this is running almost analogously to what we saw in our previous ANOVA examples. So in the CRBD and the one-way ANOVA case, we're using the DF for interaction, which is 3, and we're using the DF for error, which is 24. So now we're actually just isolating the components of the two-way ANOVA table, and we're effectively just working with the source line for the interaction. Okay, so now we have to look up this critical value. Okay, so we need an F table that's going to give us 3 and 24. So 3, 24. Oh, page 5. Sorry. Okay, there we go. Okay, so we have 3 degrees of freedom in the numerator. We have 24 degrees of freedom in the denominator, and we have 0.05, which is 3.01. So our critical value here is 3.01. So the F statistic is clearly inside the rejection region in this case. Right? Okay. Now in the second example, or if we were to take the p-value approach, we have F equals 7.452. Okay. So now, if we go back to our t-table, we're working in the same column of values here. So we can see that 7.452 is larger than the largest listed value, which means that our p-value is going to be less than 0.005. So here we can just, I think we've seen lots of examples of this, so we'll just say p-value is less than 0.0. Okay, now based off either approach, we can say that the null should be rejected because the test statistic is in the critical region or because the p-value is less than the significance level. And then on step 6, we can conclude by saying at the 5% significance level, the data provide sufficient evidence to suggest that there is an interaction effect. Any questions?
I have a question.
Please.
For the SSA or SSB or SSAB, there's like the BR, AR, and R. Is that a variable or like
So,
for the formula
yeah, so,
calculation?
right, so little a is the number of levels of factor A. So little a would be 4 in this particular example. Little b is the number of levels of factor B. So little b would be 2 in this example. Little r is the number of replications that exist for each treatment combination. So in this illustration, little r is equal to 4 because at each combination, we have 4 different measurements. So the formula that you are talking about would be a formula to compute degrees of freedom, I think, for the error term. And it would make use of each of those values. Well, I guess it would be in the sum of square. Does that help?
Could not really.
Okay, so which part is confusing you?
Wait, so little a is the number of factor A.
Is the
So
number of levels for factor A. Yep.
okay, and then little b is okay. So it's like the it's like the club is like, and then the brands are the. Okay, I understand that now.
Okay, yeah, so the brand would be factor A and the club
Yeah.
would be, yep.
Okay, thank you.
Any other questions?
I actually do have another question.
Yep.
What, like, say you just wanted to make like factor A the clubs, would that be possible, or are you supposed to have like A the more
Yeah.
number?
No, you can do it the other way around if you want. You'll get the
Okay.
exact same result. Yep. Any other questions? Okay, so if there's no questions, we'll continue to work through the tests from the ANOVA table. So in part A of this exercise, we did the model utility test. The model utility test gave evidence of a treatment effect. So the overall test of the system basically said there's evidence that there's some difference in means in this system. In part B, the part that we just worked through, we did the test of the interaction term. The test of the interaction term has given us evidence that there is an interaction effect. So there's some treatment combination that has a mean that's different from another treatment combination. Now what we're going to do are the two main effect tests. So we're going to have a test for the club type and a test for the brand type. Doesn't matter which order you do them in. I'll just go club, or I'll do brand first because that's factor A in the table, I believe. Okay, so we're going to have for brand, step 1. So here we're basically going to have H0 beta 1, or sorry, alpha 1 equals alpha 2 equals alpha 3 equals alpha 4 versus HA. Not all brand means are equal. Then on step 2, we'll have our significance level. Then on step 3, we'll pull the F value out of the table. So if we go back to slide 25, for the golf ball brand, our F value is 7.791. Okay. Okay, so then on step 4, we can take either the critical value or the p-value approach. Just to save a little bit of time, I'll just skip the illustration because we've seen lots of these at this point. Okay, so we're going to have a critical value on 3, 24, and 0.05, which we actually worked out above to be 3.01. And then our F statistic is 7.791. So the p-value here is also going to be less than 0.005 for the same reason as was shown above. Now, just to avoid confusion, the 3 that's being utilized for the critical value here is the degrees of freedom for the club, for the golf ball brand. Okay, so it just happens to work out that the brand and the interaction have the same degrees of freedom. But I am using the DF from the ANOVA table for the brand type in my first slot. Okay, and then we will reject H0, and then we will say at the 5% significance level, the data provide sufficient evidence to suggest that the that there is a brand effect. Okay. And this would really be the same thing as saying that there's an evidence of a difference between the means for each golf ball brand. But technically we're testing like the effect of the brand. We have the alpha 1 to alpha 4 in the null. So we're not directly testing the means, but this is the same consequence in the end. Oh no. Bad use of space. Okay. Sorry, one sec. I'm just gonna move some stuff around here. Okay, now we have to do the same thing for the club type. So that test is pretty much going to be identical, except we'll have a different degree of freedom. So for the club type, we'll have S1, H0, beta 1 equals beta 2 versus HA, not all club means are equal, which in this case is really just beta 1 not equal to beta 2 because we only have two club types. Okay, then on step 2, we have alpha equals 0.05. And then on step 3, we have F is equal to. Okay, and then from the ANOVA table, the F value here is 936.752. So pretty overwhelming evidence, I'd say, against the null hypothesis in this case. All right, and then on step 4, so our critical value would be 124, 0.05, which from the ANOVA table would be 124, 0.05, 4.26. So the critical value in this particular example is 4.26. And then I think it's pretty obvious that the p-value here really is going to be basically just 0. Because if you have an F value of 926, I mean, you're not leaving very much area to the right. So the p-value in this case is basically negligible. So we certainly have evidence against H naught. And then on step 6, we can say at the 5% significance level, the data provide sufficient evidence to suggest a club effect. Yeah, you can think about it that way, Jennifer. The tests are very much a one-way ANOVA 3 different ways, like in terms of the structure of the tests. But I think that it would be worth pointing out that what is different is how the total sum of squares is being decomposed. So if you compare the one-way ANOVA decomposition to the two-way ANOVA decomposition, you can see that you're taking the same total sum of square and you're now breaking it into 4 components rather than 2 components. So as a result, what you're actually doing is soaking up a lot of the error sum of squares into the other 2 terms. So one of the fallouts of that is basically when you use a two-way ANOVA, you need to have a large sample size because otherwise you're not going to have enough degree of freedom to allocate to the different terms. But in terms of structure of the hypothesis test, what you're saying is not wrong. Any other questions? The double squiggle is the approximately single symbol. So when you see, so this means equal. This, like the tildes means, sorry, it means approximately. I don't have room for it though. So yeah, and just for clarity, like the p-value will never be exactly equal to 0, but it's this particular case, it's going to be 0 probably for like many decimal places. So it's essentially 0, even though there will be eventually some value that is non-zero after many decimal places. Okay, so the last thing that we're going to do is talk about interpretation of the interaction diagram for this particular experiment. Okay, now this is an interesting exercise, I think, because the interaction diagram here isn't quite as simple as what we had seen or what we saw in the earlier examples. So we have 4 levels for golf ball brand and we have 2 levels for club type. We can still compare the diagram in a very similar way to what we saw before. Okay, so for example, if we take the average for all of the drivers, we have a value that sits right about here. Okay, so this is 233.75. And then if we take the average for the golf ball brands, we have a value that sits right about, or for the 5-iron, we have a value that sits right about here. Okay, so the interaction diagram for club type is saying yes, effect. For the same reasons that we discussed before, we can see that there's a difference in the mean of the driver distance and a distance in the mean of how far the ball travels for the 5-iron. So that implies club effect. And obviously from the ANOVA table, we know that this is a very significant effect. Now, the truth is, in the context of an actual golf type experiment, comparing the distance traveled by a 5-iron to a driver should result in a significant difference in average ball travel. The driver, by design, is meant to hit the ball further than a 5-iron. So this result shouldn't be overly surprising. And actually, you might argue that the club type is a confounding variable in this experiment because we know that it's going to cause a difference in means. Okay, the second thing that we can do is compare the 5-iron distance or the golf ball brand distances. So in this case, we're going to find the averages of each stacked point. So for golf ball brand A, our average is right about here. So this is 199.8625. For golf ball brand B, we're going to find an average right about here. This is 208.2. For golf ball brand C, we're going to find an average slightly below that. Okay, so this is 205.1375. And then for golf ball brand D, we're going to find an average down here at about 195.125. Okay, now what we would say here for brand type, it's clear that the means are not identical, right? So we would probably say, yes, there is an effect present. But it's also clear that the differences the balls travel for each brand type are not significantly different. Well, I shouldn't say significant, but the distances, like the actual differences themselves, are not that great. For example, the largest discrepancy in average distance traveled is between golf ball brand B and golf ball brand D, which is only about 13 yards. So the question becomes, the interaction diagram gives us some evidence that there is potentially a brand effect because the balls are traveling, at least some comparison of the golf balls are traveling a different distance. But is the difference between these averages enough to drive a significant difference? Then from our ANOVA analysis, we know that this difference would be considered significant because we rejected the null hypothesis for brand effect not existing. But now what we would be interested in doing is saying which of these golf ball brands are actually significantly different from one another in terms of average distance traveled. Most likely, golf ball brand B and golf ball brand D will be significantly different. But it wouldn't be surprising if golf ball brand B and golf ball brand C were not significantly different from one another, because we can see the average distance traveled there only differs by about 3 yards. So that's where the multiple comparisons would come into play. Okay, the last thing that we would want to do is talk about the interaction effect. Okay, interaction again is basically described by non-parallel sequences in the data or in the interaction diagram. So when we look at this interaction diagram, what we would want to do here is essentially break it into segments. So if we compare segment A to segment B, we can see that the line connecting AB for the 5-iron, so the dashed line, is a little steeper than the solid line connecting AB for the driver. So this implies a weak interaction. Okay. So they're almost parallel, but the one is slightly steeper than the other, so that would imply a weak interaction. Here, we can see that they're actually going in different directions. So the solid line is sloping up, the dashed line is sloping down. So we would expect to see interaction here. Now in the third case, these lines almost look parallel, except that the solid line is just has a slightly smaller slope than the dashed line. So again, we would be inclined here to say a weak interaction. Okay, so when we study the interaction effect, we would say, yes, at least a weak interaction is present. But then the question again becomes, is there a statistically significant interaction between the treatment combinations? Or is there a statistically significant difference between the mean of each treatment combination? According to the ANOVA, there is. The issue again with this experiment is that interaction could actually be driven by the difference between the driver and the 5-iron. So it's very difficult to say for certain if we can attribute the interaction to a particular treatment combination, or if we should just contribute the interaction effect to the fact that we're comparing a 5-iron and a driver, rather than say comparing 2 irons from a given set of clubs. Now, there is an interesting result that appears for golf ball brand C, because we can see that the direction that the ball travels, or the distance the ball travels, does decrease for golf ball brand C compared to the distance that golf ball brand C travels when hit by a 5-iron decreases compared to the distance golf ball brand C travels when hit by the driver. So that opposite effect could potentially lead to a statistically significant difference that would be of interest to us. Okay, does anyone have any questions? So the last thing that we want to do, since we have rejected the null hypothesis for the main effects and the null hypothesis for the interaction effects, is then go and conduct multiple comparisons. So we want to determine where the differences lie across each main effect, so the brand and the club, and then across the treatment combinations for the interaction effect. So multiple comparisons for the two-way ANOVA are going to work in the exact same way that they worked in the case of a one-way ANOVA or a CRBD. We're going to start by declaring our overall experiment-wise error, which would be the same as the significance level utilized for the F-test. And then we are going to compute the margin of error for each comparison, which will change depending on which means we are comparing. Okay, so for example, when we are interested in club effect, we're going to have little m is equal to 4C2, which is equal to 6 comparisons to perform. So there's club effect. So for club effect, we'll have choose two. Okay, we have one comparison that's of interest because we're only comparing two clubs, which are the driver and the 5-iron. So the margin of error here will be a t-value on alpha star, comma, df error, multiplied by the square root of the MSE 1 over, we'll call it the sample size for the driver, plus 1 over the sample size for the club, or for the 5-iron. I don't want to confuse anyone. Let's just call this N for B1, N for B2. So we have, sorry, C1, C2. We have club 1 and club 2. Okay, we also have to compute alpha star or alpha I, same thing. So this is going to be alpha E divided by 2 times M, which is 0.025 in this case. Okay, so our margin of error is going to be a t-value on 0.025, 24, multiplied by the square root of the MSE, which I believe was 34. Yep. And then we're going to have the sample size for each club, which is 16. Okay, why do we have 16 for each club type? Well, if we go back to the original data set, the sample size for each club is the total number of observations that were hit by that club. So for the driver, for example, you have 4 sets of 4 replications. 4 times 4 is 16. So the sample size for the driver is 16, and the sample size for the 5-iron is also 16. So we're using all of the observations that were hit by that club. So that's where the 16 comes from in that calculation. Okay, so this is going to give us, well, we can actually look up this particular t-value, but usually, obviously, we'd have to estimate them. So in this particular case, our t-value is going to be on 0.025 and 24, which is 2.064. Okay, so we would have 2.064 multiplied by the square root of 34, 1 over 16 plus 1 over 16, and that gives us 4.255. Okay, then for brand effect, so now we would have 4 choose 2, which is equal to 6. So that means that our alpha star value is going to be alpha E divided by 2M, which is 0.05 over 2 times 6, which is 0.0083. Okay, so now we're going to have a t-value on 0.0083 on 24 multiplied by the square root of 34 times 1 plus 1 over something. Okay, so what we need here are the sample sizes for each comparison of the brand types. So if we go back to the original data set, we can see that for each brand, we have 2 sets of 4 observations. So that means that little n-A is equal to 8, little n-B is equal to 8, little n-C is equal to 8, and little nd is equal to 8. So for each multiple comparison, we are comparing sets of 8 observations. So in our computation of the margin of error, we would have little 8 here. Okay, if we wanted to find this value using the t-table, we would have to use the value in the last column, t 0.005. I actually just computed this using software so I could get the exact value. So I'll just tell you that this margin of error should be 8.382 approximately. But as per usual, if on an assignment we had to work this out, we would just have to use the t-table to get an approximate value. Okay, so we can approximate with t 0.00524. Okay, and then on part C, so on part C, we have 8 treatment combinations. So that gives us a total of 28 different comparisons that we have to perform. So here we would have alpha star is equal to alpha E divided by 2 times 28. Okay, so this is going to be 0.05 over 2 times 28, which is 0.001785714. All right. So now our margin of error is going to be a t on 0.001785714 and 24. And then we're going to multiply by our MSE. And then in this case, the sample size for each treatment combination comparison is going to be the number of replications at each treatment combination. So for example, for driver A, we have 4. For driver B, we have 4. For driver C, we have 4. Okay, so N driver A is 4, N driver B is 4, etc. So for the treatment combination comparisons, we're always comparing sets of 4 values. Okay. And then again, we would be forced to approximate this t-value with the same value that we used in part B, but the exact margin of error here would be 14.483. All right, so you can see, that the way we perform a multiple comparison falling out of a two-way ANOVA is pretty much the same as how we perform a multiple comparison falling out of a one-way ANOVA. The only difference is we have to change the sample sizes that are being utilized within each comparison, depending on if we're looking at main effect A, main effect B, or the interaction between them. So we have to have knowledge of the number of levels that are being used for each main effect and the number of replications in order to work out the treatment combination effects, or the treatment combination sample sizes and the main effect sample sizes for the multiple comparisons. Does anyone have any questions?
I have a question.
Yeah.
Is the experiment-wise error rate like the error rate for like the overall experiment, and then the comparison-wise error rate is like the error rate to a specific comparison?
Yeah, so the experiment-wise error rate is the okay, so alpha is the significance level, which is experiment-wise error rate. This is also the probability of a type 1 error. So we're declaring our type 1 error for the entire experiment. The individual error rate is the error rate for each comparison. And we have to reduce that because it's a compounding error. So if we don't reduce it, we will end up with an experiment-wise error rate that's greater than what we actually want.
Okay. So like then the comparison wise error rate is like the probability of type 1 error happening in the specific comparison.
Exactly.
Okay.
Exactly. Any other questions? Okay, so there's just a little bit of time left. The last part of the lecture set, oh, are these part of the quiz? Yeah, so they'll be part of quiz 3. Quiz 2 covers lecture sets 4, 5, 6. Okay, so the last part of this lecture set just gives the results from the multiple comparisons. So in this particular case, we're using the line graph notation to illustrate the results. But all of these results are done in the same way. You take the mean, the difference in the means for the comparison of interest, and then you check to see if that value is greater than the margin of error. And if it is, you have no evidence of a difference. So all of these results fall out of the same rules that we've utilized for the completely randomized block design and for the one-way ANOVA. Okay, so this diagram here, every brand that's connected by a line indicates no difference. So we can see here that golf ball brand A is not different from golf ball brand B, C, or D. So there's no evidence of a difference in the distance the ball traveled for golf ball brand A compared to the other brands. We can also see that golf ball brand B and golf ball brand C are the same as well. Therefore, this diagram here is showing us that at the 5% significance level, there is evidence of a difference between average distance traveled by golf ball brands B and D and C and D. Okay, because those are the only two brands that are not connected. We can then see that for the club type, we have an obvious difference between the distance traveled when hit by a driver and a 5-iron. So you can see that for club, there's nothing connecting driver and 5-iron, which means that there's significant evidence of a difference between the distance traveled by the ball hit by the driver and the ball hit by the 5-iron. Okay, on Friday, we'll pick up here and we'll interpret the last diagram. Following from that, we'll talk a little bit about residual analysis in the context of the two-way ANOVA experiment. And then what we will do is we'll start lecture set 8, which is a new topic, non-parametric statistics. So we are going to talk about hypothesis testing when the normality assumption cannot be verified. And then on Monday, of course, we'll have quiz 2. So if you guys have any questions, please let me know. And otherwise, I will talk to you on Friday afternoon.